Today I want to talk about random walks, and I expect to start and finish everything about this in one day. Another extreme example of maximum compression of information. I will do it in such a way that I think you will understand. I think you will not get lost. I hope so. If that's the case, if you get lost, do raise your hand and tell me. And I want to start talking about random walks, talking about a story that happened many, many years ago. It's a very good story. And it serves as, I think, a good backdrop for what I'm talking about today. This happened even before I was teaching APM 466, a few years before. It's when I was starting to work in finance, and one of my students, I'll summarize the story and I'll paraphrase it a little bit so that you understand, was at a very similar stage as we are now. He had just learned about the dynamic asset pricing theory, and so which is what we reviewed last week. It wasn't in this example, it was something similar to this. And we had an option price. We wanted to price the option with a certain stock underlying. And as probably some of you, he became very engaged in these ideas, and he realized, he thought that he could do what we did here, which is let's go step by step. Let's do the backward propagation, which is the method that we saw here last day. Every time we do that, we get a replicating portfolio, we get an option price, and we can move back into the option price today, the replicating price today, sorry, the replicating portfolio and the option price today, and that would be the end of it. And so with that, as I told you last week, he was very energized by this. I said, oh, I can do this if I increase the number of steps to a very large number. So he went and he encoded this into a computer, and he did it more or less like this. He did the following model. There's going to be a mistake in what I'm telling you, but the mistake is what matters today. Today we're going to learn from a beautiful, absolutely beautiful mistake. So he codified the stock movements from one day to the next as follows. He was right. It wasn't Python. Python did not exist at the time. It was in C++. But he created a tree. The tree was encoded as follows. At every point in time, as T stands for time, you have a certain stock price. At the next point in time, you're going to have a stock price which is going to go up or down by a fixed amount in exactly the model that you have here. At this point, two models you could choose. You could choose the one where the stock price is multiplied by 1 plus a number u, or 1 minus a number u, that makes it go up and down. Or you can multiply by 1 times u and divide by 1 plus u. It looks like a slightly different model. You know by Taylor's theorem that these two models are very, very close to each other. When u goes to 0 and the number of steps goes to infinity, this should probably have no real impact. That was his assumption, and he was right in that assumption. It wouldn't matter how much you model that. So he was right there. And this was his first programming exercise in doing backward propagation. Because of that, he also made a u time independent, which was also the right choice, and independent of the stock price, also the right choice. He picked a 1 year time horizon, also a good choice. And with that, he was on his way to do a very nice model for what this exercise would be. You hardwire a number n, which is the number of steps that you have in the future, the number of trading periods in 1 day. Everything was good. For u, what is the value of u? Again, look at that. U is the value by which the stock can go up or down every time step, every day, every whatever amount of time you choose to parameterize your model with. So at this point, he made a choice. He said sigma will be sigma is the volatility of the stock. It's something that exists out there, and therefore the changes, the infinitesimal changes that we have in price should be proportional to the volatility, which is true. So then he said u is going to be a number which is either sigma divided by n on the upside or minus sigma divided by n on the downside. Okay, so this was the choice that was made. Okay, this was very important. This is a very, very important decision, and this is rooted on two concepts. One concept is, which is right, that the volatility is something that matters, and the other is that dividing the volatility by the number of steps looked reasonable at the time. As we're about to see, this is the mistake he made. But right now, let's not worry about that. Let's continue with his argumentation, which is very nice, very interesting. So at each branch, you calculate the risk-neutral probability of going up and down. And then the answer is a half. Why? It's a half because you can see that the value of the stock is equal to the equal weighted average of the values when the stock goes up or down. See, this equation holds. That means that the risk-neutral probability is a half. Very smart. That's right. Does everybody understand what I'm doing? Is all clear? Yes? Okay. So if that's clear, the risk-neutral probability is a half, then you can do the backward propagation in a very simple way, which is at every step in time, the option price will be equal to a half of the stock value at the nodes that go after. That clear also? Yes. Okay. So then you can obtain the replicating portfolio also very easily by solving a system of two equations with two unknowns at each of the nodes. So everything is good. You can program all of this in your favorite programming language without a problem. So that's what it did. What's the problem? The problem is what will occupy us for about an hour today. And this is what we're going to fix, because once we fix that problem, then there will be no problem to make this process we just saw here even going to infinity on a theoretical basis. And then we'll have a beautiful mathematical model. We have the ability to write computer code that will work and will converge to a number, and everything goes good. But in his case, this is the problem he encountered. He saw that either his algorithm would either not converge or always converge to a trivial answer, 0. And he thought he made a mistake. He debugged the code, checked here, checked there. He didn't find a mistake. I came to me and I told him, yes, no, you did not make a mistake. Everything you did is correct. And the key to understanding what's going on is the central limit theorem. Now, I assume that most of you have seen it, but I'm not going to assume that you know it or that you even remember it. I'm going to tell you what the central limit theorem says. And I'll review all of that for you today. Of course, it's better if you know what it is. And what's going on is here. What's going on is this. When we patch to the continuum on a stochastic problem, it's very different than if we go to the continuum on a classical mechanics problem or in the classic calculus context. Stochastic calculus and traditional calculus differ in one very important thing, which is the purpose of what I want to explain to you today. To understand it, let me ignore the fact that stock prices are always positive. I'm going to achieve that by considering the logarithm of the stock price. That gives me another number x, which is just as random as the stock price. So allow me to consider the number x for a minute. And note that because of our model, s was multiplied by a number or another as we go from one node to the other. That would mean that x is the same value as we had before plus a certain random variable. So that random variable x would be the logarithm of 1 plus u or 1 minus u. So it's just a number. And we're not going to care too much about that number now. And this starts to look similar to something that you know, because this is telling me that the logarithm of the value of the stock is going to be an accumulation of random experiments that I add at every point in time. So let me say that x is the result of a coin flip. The risk neutral measure was 50-50. That's exactly a coin. So we can use the coin analogy here and to say that the random variable x is going to be a coin flip with outcome equal to log of 1 plus u or log minus u, which you know is u. Okay, we can tailor approximate logarithm of 1 plus u to be u. So this is because the logarithm of 1 plus u is very close to u. That's Taylor's theorem. That's the reason we say I do a coin flip, and if heads shows, I give you u units, and if tails show, I give you minus u units. I hope that's clear. And this makes a connection with something that you already know, which is the results of a sum of sequential experiments. Okay. So this is how we can write the experiment that we're running, and these outcomes resulting from the coin flips are going to be independent, identically distributed sequence of coin flips with mean 0 and standard deviation equal to u. I hope it's all clear. And by the central limit theorem, we know that x will converge to a Gaussian distribution with mean x naught, because that's where we start. Note that all of the terms here, they add a mean which is 0. So the mean of the sum is 0. Therefore, the expectation of xt is going to be x naught. That's by the central limit theorem. And what's the standard deviation? This is the key. What is the standard deviation of that sum? The standard deviation of this sum is u times the square root of n. The square root of n is the number of time steps I have. Is that clear? This is the critical point. By the central limit theorem, this has a standard deviation of u times the square root of n. Not u times n, but u times the square root of n. And this is the key. Because we had chosen u to be sigma divided by n, in other words, u scale like 1 over n, we see that x does not converge. The time steps for u were too small, and that sum converges to 0. Do you understand that? This is the critical observation. It's rooted on the central limit theorem, and it's the mistake he made when he wrote the computer program. This computer program will not converge. Well, it converges to 0. The random walk that we have converges to 0. The stock price will converge to 0. In other words, the stock is not moving. The computer will know that. The computer will see that the stock is not moving, but you don't, because you're just implementing blind calculations on the computer. I hope this is clear. We have reached a point of knowledge in our hill climbing exercise today. I would like to give everybody a few seconds to ensure that you understand what I'm talking about. And if not, to ask questions. Write in the chat, whatever you want. This is a critical point. Okay, I'm assuming it's clear. I'm going to do this from many different perspectives, like the 33-cent game. Although I'm going fast in explaining all these things, I will use different perspectives to ensure that we understand everything that we're doing here. So the fix was simple, but deep. The key is to take my unit U, the amount that I make my stock go up and down by, to make it proportional to 1 over the square root of n, not 1 over n. In other words, to make U equal to sigma divided by the square root of n. Sigma is a stock-dependent volatility, and we need U to scale like 1 over the square root of n. See, the effect of this, because n is very large, is that my steps U are very, very big. Much, much bigger. Infinitely bigger than the one you would expect from traditional calculus, where you expect U to scale like time. U scales like the square root of time. Let's put this into the context of a random walk. And let's see if you can follow my argument here. I'm in Germany right now. You're in Canada right now. Let's say I take steps. I can walk over water, and I can take steps from Germany to Toronto. I'm going to simplify the numbers. I'm going to say that I take 1 million steps. In 1 million steps, I can be in Toronto. I have very big steps size, okay? In 1 million steps, I can be in Toronto. And I'm going to walk randomly between where I am to where you are. 1 million steps. Each step is going to be, let's say, 10 centimeters, just to say something, okay? If every time I take a step 10 centimeters forward, I flip a coin and I decide if I go 10 centimeters to the right or 10 centimeters to the left, with what accuracy will I end up in Toronto? I'm assuming 1 million steps, 10 centimeters each. That's my assumption. I mean, I'm assuming Toronto is a bigger distance than it is. So 1 million steps is easy. That's 10 to the power 6. And 10 centimeters is it's a reasonable number. What would be my distance or my deviation from downtown Toronto, from the University of Toronto? What would be my deviation? My standard deviation, by the central limit theorem, my standard deviation is 10 centimeters. I have a million steps, so it's a million steps divided by the square. It's the square root of a million, which is 1,000. That means I'm going to have about 100 meters variation to the center of Toronto. And if instead of taking a million steps, I take 100 million steps, I will be within a meter of downtown Toronto. You see what happens? If my scale in space is the same as my scale in time, the more steps I take, the more accurate my arrival place will be, and my model is actually not stochastic at all. It looks stochastic because I'm flipping a coin at every step, but it takes so many steps, and my variation to the right and to the left is so small that by the time I take that many steps, say 100 million, my distance from the downtown Toronto is 1 meter. And if instead of 100 million, I take 10 billion, then I'm within millimeters of downtown Toronto. It's too small. That's by the central limit theorem. The central limit theorem says that there's a lot of cancellations between my randomness going up and down. The cancellations mean that my model is very accurate, which means I am actually not modeling anything random. That's what we're doing, and that was the mistake. The mistake is it can be understood now. Let me say this in a different language and hope that with all of these different approaches to the problem and the solution, we understand what I'm talking about. The outcome either of the stock evolution game or my walk into Toronto exercise, they're both the same, is a superposition of random variables, n of them. And each random variable is random with a standard deviation 0 and a standard deviation sigma. So as I add them all up, my expected outcome for S, the sum of all of those steps, is if I move dx in the x direction, it'll be n times dx. And if I move dy in the y direction, it'll be Sn times dy. So the final location where I will be n times dx and S times dy. If n times dx is the distance between here and Toronto, then that's where I am on the x direction. But on the y direction, my deviation to the north or to the south is going to be given by S and dy. And with the numbers that I chose earlier, they're just too accurate. So the central limit theorem says that the probability that my sum normalized by the square root of n will behave like a Gaussian distribution. That's the central limit theorem. That's where the square root number comes from. And that's equivalent to saying that dx is like 1 over n and dy should be like 1 over the square root of n. Or dx should be like dy should be like the square root of dx. And then it converges to a normal distribution 0, 1. And then I can introduce a volatility. So if I take a million steps, 10 centimeters each, towards Toronto, but my deviation when I flip a coin is not 10 centimeters, but it's the square root of 10 centimeters, about 0.3, about 30 centimeters, then I will end up at a distance from downtown that when I take more and more and more steps will be the same, will not change, will converge, and will converge to a normal distribution away from downtown Toronto. And the distribution away from downtown Toronto is governed by a Gaussian distribution with a standard deviation sigma. Sigma is the ratio between my dx and my dy. So I just said the same thing in the context of the central limit theorem. And I hope you all understand this. Some of you may have seen the formal derivation of this, and then you've seen a different approach, but the answer is the same, where we get to this. And if you've never seen this, this is something that you can understand in just a few minutes. As I told you, you have to make certain, you have to be generous in the way that you understand the mathematics that I'm telling you, but this should be clear. Okay, I want to address this phenomenon from yet a different perspective. And this is the perspective that was introduced by Einstein in 1905. Yet a different context. He was not walking from Germany to Toronto. He was not looking at stock price evolution. He was looking at heat transfer. Footnote: this model that I'm telling you that Einstein did in 1905, similar version was done by Bachelier, a French mathematician, in the year 1900. He was a student of Poincaré. Basically, it was the same. Mathematically, it was the same. Bachelier. We don't talk about Bachelier very much in this course or in finance, because he did very nice mathematics, but he had no finance component. He applied mathematics to financial objects, but there was a very. I'll tell you what his problem was, what his mistake was somehow. Okay, but so let me go to Einstein's theory. So what Einstein's theory says is the following: if I want to understand heat transfer in a one-dimensional heated rod, I introduce the temperature concept. The temperature of two particles at a certain point in time, this is at time t, this is at time t plus dt. That's my heat distribution. Then what he argued is that if the heated rod is isotropic, which means the temperature doesn't care if it goes to the right or to the left, goes to both directions equally likely, then the temperature at the point between two neighboring molecules will be the average of the temperature of those two molecules. In other words, the temperature moves with equal probabilities to the right and to the left. That's just that. Now, look what happens if I take this hypothesis into math. That says that the temperature function u at time x will be equal to 1/2 of the probability to the right, 1/2 of the temperature to the right plus the temperature to the left. That's what it says. This is my assumption, how diffusion works. So if that's my assumption, how diffusion works, then let me take this equation and I'm going to add to the right and to the left of this equation the amount u of x comma t. Exactly the temperature in the middle at time t. What we have on the right is perhaps easily recognized as the discrete Laplacian, the discrete second derivative, of course multiplied by dx squared. And what you have on the left should be easily recognized as the discrete gradient with respect to t, of course multiplied by dt. So the heat equation that many of you have studied when you study differential equations happens precisely because dx is equal to dx squared. Dt is equal to dx squared. Dt is proportional to dx squared. There is the specific heat capacity, which is the proportionality constant between dt and dx squared. But barring that, looking at the mathematics of it, dt and dx squared, they cancel each other out, and we get the very well-known heat equation. So once again, the argument I gave you, these implications or these derivations from the central limit theorem give us the right time scale when we're doing stochastic diffusion. So this is the third perspective that I'm introducing these concepts in. I hope all three are clear. I suspect you have seen at least one of them in the past, but maybe not in the context of stock prices, which is what I'm doing today. I'm going to look at stock prices from the perspective of diffusion, exactly what I'm talking about here. And this is the right way of the dynamic asset pricing theory, the way we did it last week. If you want to increase the number of time steps, what suddenly matters is the ratio between the increment in price and the increment in time. That ratio is governed by a fundamental relationship. The increase in price has to be proportional to the square root of the increase in time, infinitesimally bigger. Once we get that settled, then we can start to do the theory of random walks. And the passage to continuum that we have seen in the backward propagation for trees will work without a problem. So at each step in time, we're going to consider this sum of independent increments to the price by coin flips with outcome plus or minus u. And I remind you, all of this is because we're looking at the logarithm of the stock price. The result is that the price at any point in time will be represented inside your computer as the sum of an IID sequence of coin flips with mean 0 and standard deviation u. And we know this converges to a Gaussian distribution with mean my starting price, logarithm of the price, and a standard deviation u times the square root of the number of steps. And we scale u like the square root of the time increments. The proportionality constant being the volatility. Is that clear? So that gives us the fundamental relationship. All right, so this is the basis on which Ito processes are built. Ito processes, they were created not in the context of finance, they were created in other contexts. I read that one of the motivating situations for Ito, a Japanese mathematician, was how boats in a river move, because you have your deterministic direction, but then you have random disturbances around that. So to model that, he came up with something that I'm going to write here in the following way. I'm going to talk about the evolution of a certain object, could be a price, could be a physical object, which is governed by the superposition of now two processes. One is classical, where the movement happens with increments which are proportional to time, and one which is stochastic, where increments happen in a way which is proportional to the square root of time. It's a superposition of a classical movement and a stochastic movement. That's an Ito process. Mu dt, I don't have to say anything about that. You've spent your life looking at that since you learned calculus. dw is what for some of you may be new. We saw that for the first time in this course, and we think of that as an infinitesimal coin flip with probability 1/2 of giving you plus square root of dt or minus square root of dt. That's an Ito process. That's all we're going to see about Ito processes here. For sure, there are many things which I am not telling you, which are being hidden. And if you care to do this in a mathematically correct way, you'll have to read a few books. But for most of you, this is everything that you need to know today. We're not going to, but we could consider both mu and sigma to take a more complex functional forms. Mu could be a function of time, could be a function of x. Sigma could be a function of time, could be a function of x. In this course, I'm just going to take mu and sigma to be very simple. They will be functions of x, very simple functions of x. We don't have to worry, nothing very complicated. And that's going to be good enough for all of our objectives when we try to model the evolution of security prices. But these things happen in many other contexts and in many directions. Now, the basis of this is stochastic calculus, which I'm going to summarize here by considering an object, a new object, Brownian motion, which I will do a little bit more rigorously at the end of today, but I don't want it to bog down with the formalities of this. I want you to think of Brownian motion as a sequence of coin flips. At every stage in time, we get a coin flip with expectation 0 and a movement to the right or to the left equal to the square root of the time increment, dt. The result is a Gaussian random variable at a point in time where the standard deviation is given by t. In other words, the variance is equal to t. That's Brownian motion for us. I'll give you a slightly more involved definition. I'm not going to give you the full definition, the actual construction from scratch. You'll have to read some books for that. But I'll give you something which is a little bit more formal than this at the end of today. That's assuming we get there. I'm less interested in the formal derivation of this or the formal definition of this than I am in that you understand what these concepts, how these concepts are built. That's the important part. So from here, we can construct the stock price process. The stock price process will tell us that we have we have security prices. For stocks, they are never negative. For other like futures or for options, they could be negative, but not for stocks. So we're going to consider prices underlying securities whose prices are never negative. Therefore, I can consider the evolution of the logarithm of the price. And the logarithm of the price is going to evolve according to an Ito process, just like the one we saw earlier, the one which is written on the screen. This gives us a realistic model for price evolution in the following ways. First, the result is always positive. X is a number, and S, the price, is the exponential of that number. So it's always going to be positive. The price change in S is proportional to the change, is proportional to the value of S itself. So stocks which are more expensive will change more than stocks which are cheaper. So the model we're going to establish is this one. And the question that arises now is S an Ito process itself? It's clear that it's logarithm S, it's defined like an Ito process, but what is S? Is S an Ito process? And if that's the case, which one is it? So for that, we're going to present a more general context, which will make the answer to this question not just easier, also more useful, because we get to reuse that way of thinking over and over again. And the question is this: if I consider an Ito process and I take a function of the Ito process, a function which is smooth, has derivatives, a nice function. If I take a function of the Ito process, possibly a function of the Ito process n time, is this a new Ito process? And the answer is yes, it's an Ito process. But the interesting part is not so much which one is it, which I will show you. It's the fact that it is going to have the square root show up again in an unexpected way. Once I solve this question, note that if f is the exponential function, then that will tell me which Ito process the stock price follows. But I want to answer that question first. And this is a very well-known lemma. It's called Ito's lemma, which is the chain rule for stochastic processes. And it goes as follows. I'll give it to you, but then I'll justify it in a very simple way. An Ito process is given by a superposition of a classical movement with dt and a stochastic movement with Brownian motion, dw. That's the Ito process. If I take a function of my Ito process, what I get is this thing that I wrote in front of you. So let's look into that carefully. A function of the Ito process will be an Ito process itself with a drift. The drift is the classical part, the movement that scales like this, like time, and a stochastic term, which is the one that scales like this, like the Brownian motion, as you have here. Now, in this expression, there's two terms: the black terms and the red terms. The black terms, look at them first. They are the ones, let's look at the first equation. The black terms is what you expect from multivariable calculus. F is a function of x and time, so its derivative will be the partial with respect to f times dt plus the partial with respect to t times dt. This is the chain rule for functions of two variables. That's the black part. But then I wrote the part in red. The part in red is the interesting one for us today, because when you apply Taylor's theorem to this, there are many more terms which we typically ignore because they are of lower order. For example, we ignore dx squared because dx squared is of low order, so it does not show up in the derivative. But now, in this stochastic context, dx squared contains three things. One is dt squared, which indeed is very small, we throw away. The other one is dt times dw, which indeed is very small and we throw away. But there's another one, which is sigma squared times dw squared. But dw squared, we just saw, is not negligible, it's dt. We cannot throw it away. It's dt. So you have to observe that when I go to the second line here, this element turns into that because dx squared is dt. Okay? So this is the chain rule for a stochastic motion. And it's there because of our assumption that dx squared was proportional to dt. So this is Ito's lemma. And Ito's lemma makes stochastic analysis be radically different from traditional calculus. It's going to change many, many things for us. And it's the basis on which the theory of heat transfer looked at it from the diffusion perspective that Einstein took works, and is the perspective, or is the context in which the Black-Scholes theory works for us when we try to take the limit of our dynamic asset pricing theory when time increments go to zero. Okay, maybe I'm going to continue for a few more minutes and then we'll take a break. I want you to absorb all of this. Now, when a stock price process is given by this combination of the logarithm of the price being an Ito process and S itself being an Ito process in its own right, okay, this is the resulting Ito process that we would get when we apply Ito's lemma to the exponential. What we see here is, this is the interesting part. So I save you, these are the calculations from Ito's lemma. There's no mystery there, you can do it yourself. I want to focus on this. This is the interesting part in our discussion, because what this shows is that the stock price process, of course, you see it's proportional to the price itself. We already expected that. This is not a surprise. But here what we're seeing is that the stochastic part is the same as the one that we started with for the logarithm of the prices. But look at the drift. This is called the drift. Look at the drift. The drift is amplified by sigma divided by 2. The drift is amplified by sigma squared divided by 2. How interesting is that? So we understand this from the perspective of Ito's lemma. We went through that. I told you, and I gave you some hand-waving derivation. I'm not going to prove this. I have no interest in proving this mathematically for you. No interest. But this is something that I want you to be aware of, because this thing is something that shows up in practice. And I have an example of that. Imagine this fund. Now I'm talking about investments. I'm not talking about stocks. Imagine this fund. I have a fund. I start with $1, and then I'm very successful the month of January, and I end up in February with $2. But then in February, I lose $1, half of it, and then I end up with $1 again. Then I make $1, lose $1, make $1, lose $1, make $1, lose $1, like that forever. So every month, I have a 100% gain followed by a 50% loss. What's my average return? Statistically, my average return is 10 minus 50, 50 divided by 225. So my average monthly return is 25%. Are you surprised by that? Here I have a fund. It makes no money, and the average monthly return is 25%. Is that a coincidence, or am I lying to you? What's going on? No, nothing is going on. This is Ito's lemma at work. Why? Let's look at the logarithmic return. So let's look at the logarithm of the value of the price, and the logarithm of the price starts with 0, and then it goes up and down as either the positive of the logarithm of 2 or the negative of logarithm of 2, and I have it written there in front of you. So for sure, the average return of the logarithm of the price is 0. The standard deviation of the logarithm of the price is about 70%. So what Ito's lemma will tell us is that the drift, or the average of the price itself, is going to be mu, which is 0, is the average of the mean of the logarithmic price, 0, plus sigma squared divided by 2. What is 70% squared divided by 2? Let me ask in the chat. I need to know if you're alive. Write in the chat what the answer is. What's 70% squared divided by 2? Correct. It's 25%. So that's exactly why we see that. That's exactly that the remarkable difference between the return of a fund and the return of a logarithm of the same fund is actually Ito's lemma. This seems to pose a problem, because when you're going to invest in a fund, what number do you think they report to you? They report to you the average return of the price or the average return of the logarithm of the price? They report the average simple return. So they report a number which is bigger than you think. Well, not anymore, because now you know Ito's lemma. And you know that if the volatility of the fund is high, and by the way, the volatilities of both funds are pretty much the same, and we know that again by Ito's lemma, right? So if the volatility of a fund is high, then you know you need to discount the expected return by sigma squared divided by 2. So let that be a very simple application of Ito's formula for you now. And next time you're going to invest in a fund, the volatility is high, you already know you need to discount it. Ito's lemma, of course, has many applications, as you can imagine. But right now, I'm not interested in applications. I'm still interested in building a mathematical model. And I remind you, we're still under the assumption that everybody works for free. I need 2 more weeks of that, this and next week. And then it's over. After reading week, everybody works getting paid. So there's a question asking whether I discount the regular return by the log standard deviation. Correct. Can you find the log standard deviation without knowing the returns? By Ito's lemma, the standard deviation of the prices and the standard deviation of the logarithm of the prices will be the same. Right? It's in Ito's lemma. The drift changed, but not the drift changed, but not the stochastic part. See that? So on the table, why are there no stochastic standard deviations listed? Yes, they are listed, 70 and 75. No? I don't think I understand the question. On the table here, why are there 2 standard deviations? Well, Ito's lemma applies to a Brownian motion. This is not Brownian motion. It's an approximation to Brownian motion. So Ito's lemma will hold all in an approximate manner. That's why we see that 70% becomes 75. It's not exact. And that's why, by the way, the 25% is not exactly sigma squared divided by 2. You need to be aware that when you have a model and when you have real numbers, the real numbers may not always be exactly what the model says, right? They're just approximations. Okay, I think this is clear. I think you understand what I'm talking about. Okay? So this is perhaps the answer to your question. The results are not Gaussian. It's a Bernoulli. This is not Gaussian. So Ito's lemma will be accurate, but I mean the accuracy is impressive, right? Ito's lemma is only presumed to be approximate, but it's actually impressive. Okay, so we have climbed a very tall mountain now that will make us very powerful. And one of the results of that is we can build the Black-Scholes theory. Now, before I do that, I want to stop by, look at the landscape, and talk about, make some reflections. The first thing I want to reflect upon is the concept of a false friends. The world of quantitative finance is full of false friends, things that people believe, things that people do, which are actually not true. Not hoaxes, just things that people just. There's a lot of things that look correct but are misleading. you probably know that a little information is always a dangerous thing. I think Einstein said that, right? So what I'm trying to give you is enough information so that you are empowered to know what is true, but also empowered to know what is not true. Okay, the power of mathematics, and I think I've said it many times. I like to say it is of course it gives you ability to calculate things, discover new things, and that's true. But for most of you, when you go to work, you're not going to use math to discover new things. You're typically going to use math to avoid false leads, not to be tricked into thinking this or thinking that. And there's going to be a lot of examples of that in this course, that especially as we get to do more and more sophisticated things, especially when we talk about investments, especially when we get into the context in which people work to get paid, that I think are going to become very, very clear. Okay. All right. So I have a good sense of accomplishment that we've gone through the first hour with a very quick introduction, 1 hour introduction to stochastic calculus, focusing on what I think matters, giving you just an intuitive approach to it, but an intuitive approach which I think is rooted on some good intuition. I think it's going to be useful for us going forward. For those of you who are interested in a more rigorous treatment of this, you'll have to read a few books. They are listed in the bibliography in the course website. It'll take you a long time, probably a year, to get to understand all of those things very, very well. I compressed a year of work into an hour. I think it's pretty good. I think for most of you, this is all that's going to be required. Okay, so we're going to take a 10-minute break. And when we come back, I want to show you how this thing we developed can be turned into the development of the Black-Scholes theory. So we'll do that in 10 minutes. We are now in a good position to take our 33-cent game from the dynamic asset pricing perspective into a continuous time model. And the 33-cent game is going to become a game we're going to play in continuous time. So let me go through this. This is the biggest assumption. This is everything we have already seen expressed mathematically. So I'm going to assume a derivative similar to our 33-cent game. It's a European option. Think of it as an option where I will pay you everything in excess of a certain strike price for my stock. We in the past we have said a stock which is $1 today, and I'll pay you everything in excess of 75 cents, or everything in excess of $1. That's the strike price. Everything above that I will pay. The stock will move according to geometric Brownian motion, or in other words, ds over s is an Ito process, or in other words, the logarithm of the price is an Ito process. Note that in this case, I'm assuming ds over s has a drift equal to mu, which means that the logarithm of s, the logarithm of the price, will have a drift which is mu minus sigma divided by 2. Also an Ito process. That is how I model my price evolution. And my option is going to have a payoff at maturity time t. And I'm going to assume that time moves in a continuous fashion between now until capital time t. The payoff is a function of the price at maturity only. And our objective is to find the price before maturity. My objective is to find the price, which I will denote by f of the stock price, comma t. So this is the exact same approach that we had when we did our option pricing. We had a tree, and the tree had different time steps and different price at every node. That's now expressed by the value s and the value t. So this corresponds to the nodes in the tree, except now we don't have a tree, we have a continuous time motion, a Brownian motion. And what I want to do is I'm going to tell, as I did in the 33-cent game, I will just tell you what the replicating portfolio is. Just that in this case, the replicating portfolio is going to be given with variables. I want to say I hold A units of stock at time t, and I'm going to hold B units of bond at time t. I call them A and B. B for bond, A for stock. Same as we did for the 33-cent game. It's just that in this case, there's going to be an explicit dependence between the number of stocks and the number of bonds and the price of the stock and the time at which we look at the price of the stock, T. And this is going to be such that the option will be replicated by the portfolio. So the price of the option will be equal to the price of the replicating portfolio at all times for all possible prices S. And at maturity, the price of the option will coincide with the payoff of the option, F sub capital T at S. So everything that you have on this page is the reproduction of the context in which we developed the 33-cent game. You see that? Everything is the same, exactly the same approach, number of stocks, number of bonds. The only difference is that now everything is going to depend on continuous variables S and T, and S moves according to a well-defined Ito process, the one that you have on the screen. But everything else is the same. So there's going to be a financial argument that will make everything work. And the financial argument is this. Just like when we played the 33-cent game, I knew in advance what the price was, and I knew in advance what the replicating portfolio was, and I just told you what my replicating strategy would be. I'm going to do the same thing here. I'm going to tell you what the replicating strategy will be, and it is that I hold a number of stocks at all times, which is equal to the partial derivative with respect to S of the option price. Now you may be thinking, hey, wait, how do you know the option price so that I know what the stock price is? I say, no, I don't know the option price. I'm a mathematician. I don't know the option price. I call it F. And I don't know the number of stocks, except I will set them equal to the partial derivative with respect to S, or whatever it is that the option price is. And you may be asking, why do I know that? Well, I know that because, first of all, I've seen this before, but more important than that, I don't have real foresight. I'm just going to do an argument where you could derive the same thing. It's just that I think it's easier for you to understand it once I reveal what the mystery is. I think I'm right, but you will see. Just assume this is the case, and you will see that everything works. And then you could go back and say, well, I could have known that myself. So with that choice, I'm going to construct a portfolio. This is not the replicating portfolio. It's another portfolio, which is the following. It's my option minus the number of stocks and minus the number of bonds. So I'm building it like that because it's going to be slightly easier to go through the formalism. If I look at this from the point of view of the 33-cent game, what I'm doing here is I'm considering a portfolio which is the option minus the replicating portfolio. So this looks like the portfolio which is free, and that's pretty close to the truth, you will see. Okay, but that's the portfolio I'm going to be working with. The reason is I prefer to have one portfolio and not two. I have the option and the replicating portfolio, so I combine them into one. That should be a free portfolio, should be a bond, maybe not. And then I will just focus all my attention on this portfolio. And look at what's coming here. Let's not get scared. Let's go in this step by step. Okay, I'll do this carefully. So this is the portfolio, and I want to see how the portfolio evolves. I want to show you that this is the replicating portfolio. And I show you how this evolves by taking the partial derivative, by taking the derivative of the portfolio with respect to time. This portfolio is an Ito process because F itself will be an Ito process, and the number of stocks and bonds is an Ito process. And I want to see how it evolves. I want to see what kind of an Ito process it is, and I do that by using Ito's lemma. So, because the portfolio is F minus the number of stocks and minus the number of bonds, the derivative of the portfolio value is going to be the derivative of F, the derivative of the price, which I don't know, but that's my unknown, minus the derivative of the number of stocks times the stock. In doing that, that partial derivative has two terms. When I take the derivative of this has two terms. This is one, and this is another one. I break them up because financially they represent completely different quantities. So I'm coming to that. And the number of bonds that I have, when I look at the derivative of that, it also contains two parts. One is that, one is that. Here I'm using the product rule. I'm using the product rule. I group them differently because financially they are going to correspond to different quantities. So I end up with my a special term here, which I want to now argue to you that this term is equal to 0. Because what this term is, just this term, okay, just this is equal to 0. Just this term is equal to 0. Why? Because what this term means is as follows, and I want you to think about this intuitively. What this represents is this. At every step in time, like we have done in the discrete, in the dynamic asset pricing theory, I will buy some stocks and I will sell some bonds, or I will sell some stocks and buy some bonds. At every time, I do that without spending any money. In other words, it's what's called a self-financing strategy. When I charge you 33 cents for the option, and I do my hedge and I construct my portfolio, I never go back and ask you for more money, or I never return money to you halfway through the process is such that all of the money which I get from stocks or bonds gets reinvested in the portfolio. Because of that, this is the reinvested amount. Because of that, this is equal to 0. So I drop it. This is a financial argument. It's actually the main financial argument that I'm making. I have a self-financing condition. I never put more money. I never take money away from my strategy. I never ask the option holder for additional money. I charge a premium only at the beginning. And everything that I do is from the evolution of the prices of the stocks and the bonds. Now, when I consider the derivative of the stock price, I go back to my Ito process for S, and that gives me I have that term. Here. I leave it like that. And for that, I use Ito's lemma. Ito's lemma. So Ito's lemma will give me that term, and that term. That's Ito's lemma. These are the three terms that Ito's lemma will give me. All right. And then that term is just that. That's all. So the only thing I have done between line 1 and line 2 is this is equal to 0, and this I expand into Ito's lemma. That's all. That's Ito's lemma. And now I make my critical observation. My critical observation is that this cancels that. This is It's not a miracle. Notice that this is the reason why I chose the number of stocks equal to that, because I wanted to cancel these two terms. The significance of canceling these two terms is not yet obvious, but it's clear that it gives me a very interesting, very simple evolution for this portfolio. This portfolio evolves like that. The stochastic terms have disappeared. I have no stochastic terms. I only have drift, because these are the only two carriers of a stochastic term. So the reason I chose my replicating portfolio to be that is so that I get rid of the stochastic part of the replicating portfolio. Okay? Now, this is a long equation, but I think it's well understood by now. Yeah? So that's the self-financing condition. Here I use Ito's lemma. That gives me one term that will cancel my choice of the replicating portfolio. And the result of this is that this portfolio that I had evolves like a bond. Maybe it's zero, maybe it's not zero, but it evolves like a bond, which means that its evolution should grow like interest rates. And that's exactly what I wrote here. It grows like interest rates. Now, you should recognize here that this is the same argument that we did when we constructed the 33-cent game. In that case, it was very easy. I took some money from you and I used it to borrow some money and to buy stock. That's exactly that. That's the money I take from you, I borrow some money and I buy stock. That's exactly the same. Okay? So let me now make the mathematical argument. The stock part of the replicating portfolio is that. So when I put that into the portfolio I have there, this was my replicating portfolio, the one that moves like a bond, what I have is that portfolio times R, which is I have here, that has to be equal to that. So that's the mathematical argument that falls out of the observation that this replicating portfolio is a bond. So from there, we get this equation. So that can be rewritten to make it look like a diffusion equation as follows. I take the partial derivative with respect to time on one side, and I take the partial derivative with respect to price on the other side. And at maturity, both are the same. So this is the consequence of our use of Ito's lemma. This is the well-known Black-Scholes equation. And what I want to do now, I know that there is a lot of variables on the screen for you, but I want to reflect on everything that we have here. So let me do the following. So from here is easy, right? There's no mystery here. Let me tell you some surprising observations about this equation. The first one is, where is the drift mu? Where is mu? Where is the drift mu? It's disappeared. Why did it disappear? It disappeared because mu is the analog of my statement when we played the 33-cent game that the stock has a probability of 50% of going up and down. Is the analog of that. And by now we know we don't need that. In fact, the stock should grow at the same rate as the bond because the risk neutral measure should price both at the same rate. So mu has become R. It's right there. It's not mu, it's changed into R because the real world measure has changed into the risk neutral measure. That's why it has disappeared. Now, you may not care why it has disappeared because we follow the argument and the argument tells us we're correct anyway. So that's the first observation. That's a financial observation. The price of the option is independent of the drift of my stock. Now, second observation is some of you know differential equations. What's the difference between the heat equation and this equation? There's some similarities and some differences. I'm interested in the differences. Let me go to the similarities first. The similarities is that I have something with respect to t, a derivative with respect to t, equal to a partial derivative with respect to price. You would have seen that when you have a differential equation, it's the highest degrees of derivatives that matter. They govern the type of equation that you have. So the lower order terms are f and r times df times s matter less. So these are the important ones. So it does look like the heat equation. Something with respect to t is equal to the second derivative with respect to x. But there's a very important difference. You see that? The minus sign. The coefficient is negative. You're right, Eric. Now, have you ever seen a heat equation which is like that? Have you ever seen that? That would correspond to a negative specific heat capacity. Have you ever seen that? No, you have never seen that. In fact, this equation has no solution. Then how come ours has a negative sign? Ours has a negative sign because in the heat equation, we have the temperature now and we get the temperature later. In our context, we know the price later and we find the price now. In other words, in the Black-Scholes context, we go backwards in time. Backwards in time compared to the heat equation that goes forward in time. So if I go backwards in time, this derivative with respect to time should give me a negative sign. That's exactly that one. This is a backward diffusion equation, whereas the heat equation is a forward diffusion equation. Look at Einstein's argument. We know the temperature now, we find the temperature later. Look at backward propagation. We know the option price later, we find the option price now. We go backwards. The backwards is the reason why we have that negative sign. And as it happened with our 33-cent game, everything that matters for the price is two financial variables, the interest rates and the volatility, nothing else. So this equation is long and complicated. Did I manage to remove a lot of the mystery behind this equation? I hope so. There's many aspects of this equation. I am not going to spend a lot of time with either of them. I will move on. There's other things that I want to tell you. Um, so maybe to remind you that this is a terminal condition, what is usually called an initial value problem or initial value condition. Initial condition here is a terminal condition. Again, because we move backwards in time. Okay. So from here, we have a differential equation. This differential equation can be solved. I'm not going to go through the solution for you. I will just tell you what the answer is. I'll just tell you what the solution is. The solution is this. And as usual, this looks like a very big formula with lots of difficult to understand objects. But I will walk you very carefully through this so that you understand why we have seen this before. Yes, we have seen this before. Some of you may be shocked to hear that, but we have seen this before. To understand why we have seen that before, I'm going to draw your attention to a certain terms here. The first term is this one. What is this? We have certainly seen this before. This is how we discounted bonds. Remember? So this is a discounting factor. That means that the option price is going to be something, everything we have here, everything, which we don't know yet, discounted to today's value. So this is the discount factor, exactly the same one that we have seen for bonds. So yes, we have seen this before. Next, this big integral. What is this? Let me argue that we have also seen this before. This is an expectation. An expectation of what? Let's look at this more closely. That's the payoff. That's the payoff of the option. Where is that the payoff of the option? That's the future price. That's how the price will grow through Brownian motion. And the Brownian motion, of course, will take us to a certain future price with a probability given by Gaussian. Of course, it's an expectation. It's the expected payoff. So if I put these three words together, this big expression we have here is nothing but the expected discounted payoff. I remind you that's how we priced the 33-cent game once we had the risk-neutral measure. So this is the risk-neutral measure. That's what's going on. The risk-neutral measure in the Black-Scholes context is the Gaussian, where we replace the drift by the interest rates. And then the option price is the expected discounted payoff. That's a log normal price. That's the key to understand why this is the payoff. The price is not normal. The logarithm of the price is a normal distribution. That means that the stock price is a log normal, meaning that it's the exponential of an Ito process. And what you see there is an exponential of an Ito process. An Ito process represented by x, and we use the Gaussian probability density as the measure against which we take the expectations. Are we all together on this? I want to make sure that we're all together. I want to give you at least a few seconds to ask a question or to say something. Is this integral solvable? That's a question. Most of the time, no. By solvable, you mean in closed form. The answer is no. It is not solvable in closed form, but we don't really care. This concept of closed form solutions it was important in the 19th century when there were no computers. Today, closed form solutions are very handy when you have to do simulations because they're a lot faster. If it takes, let's say that you had an explicit solution for this formula, as opposed to solving this with numerical methods where it may take 10 milliseconds to solve this. If this was an explicit solution, maybe it takes a tenth of a millisecond, a factor of 100 maybe. Okay, and a factor of 100 when you have to do a big Monte Carlo simulations or some of the other things that we will see, it could make a difference. Between waiting an hour or waiting 100 hours, you bet there is a difference. Okay, however, we don't really need a lot of, again, the concept of a closed form expression. For many of the applications, we can have a closed form, nearly closed form expression. For example, this one. If I'm trying to use the Black-Scholes theory to price a call option with strike K with a certain stock with the current price S naught, volatility K, and constant interest rates and constant drift. The drift is not important, but let's say it's constant drift. Then the value can be almost solved explicitly. It's the expression that you have there. The only reason it's not completely explicit is because I have to use the cumulative distribution function for the Gaussian, which is the expression you have there. Now, for many computers, this is already built into their standard function package. So this is as explicit as if I write, say, the sine function or the cosine function. Although the sine and the cosine function, the computer will have to do some work to do it because it's not a multiplication, addition, subtraction, or sum. So if you accept that the cumulative distribution function of the Gaussian is as explicit as the sine or the cosine function, then the answer is yes, here it is. It is that. And in fact, well, I have to say here we are going to use, there are two special elements which appear in the argument of the cumulative distribution function of the Gaussian, which are these quantities which they will appear again in this course in a completely different context in a few weeks. Okay, for now, let me just leave them there. They are financial quantities. You may recognize you may recognize here this term, which is the value of the stock divided by the strike price. This is the moneyness. An option is at the money when S naught and K are about the same. Is out of the money when S naught is much smaller than K, and is deep in the money when S naught is bigger than K. Okay, so that's the moneyness. This is the volatility scaled by time to its time scales. That's the volatility expressed not on a per year basis, but on a to maturity basis, and so on and so forth. Okay, that will be the risk neutral drift taking into account the Ito's formula. So all of these elements have an explanation of their own. We know where they come from, we know what they mean, and together they make up this formula, which is semi-explicit, and it allows the price of the call option. Now, this is only good for call options. For put options, this does not work, and neither does it work, for example, if I have a call option where I have dividends. This is not the right formula for dividends anyway. The Black-Scholes formula has some explicit solutions sometimes, but most of the time it does not. It doesn't bother most people, okay? Because you can solve these things quite fast in practice. So I hope that addresses your question. I'm now going to talk briefly. I will take another break. I know that what I'm doing today is very, very heavyweight, but it's a good climax of this pricing theory festival we've been having for the last few weeks. But my intention is that you never lose sight of the 33-cent game. The 33-cent game is still here somewhere, and it makes everything we're talking about work. Okay. Now, European options are options that expire at a preset point in time. They have a certain payoff and a certain strike price. This is the payoff structure for the European options. At maturity, I will pay you everything in excess of the strike price. And as I've mentioned in the past, I remind you that the subindex plus here means that when this is positive, you get what it is. And when it's negative, you get 0. In other words, the plus graph is that. Okay, it's like the absolute value, except it's not that, it's that. It's the absolute value of the positive part and 0 for the negative part. So that's the payoff, and this is the one for which we have the semi-explicit expression for the Black-Scholes theory. Okay, put options have the opposite payoff. You get paid when the stock price drops. American options, I remind you, are the ones that they have a payoff exactly as the European options, but they can be priced at any time prior to expiration. The Black-Scholes theory can be extended to deal with them. You don't have an explicit solution, but the Black-Scholes theory will also work in that context. Let me just leave it like that. If you need to know what it is, you'll have to read one of the many books that talk about that. And you also have the same considerations that we went through earlier, which is we could have optimal exercise before maturity, and so on and so forth. Everything that we saw continues to carry forward to the Black-Scholes theory. But I'm not going to talk about that. All right. Now, what I have here is a graph of, I did this, in February 2024. I did this 2 years ago. So 2 years ago, I was lecturing on this, and then I wanted to say something, which I'll tell you, these prices don't really mean anything. What I did is, I went and looked at the price of calls and puts on a certain security, probably the S&P 500. And I want you to see this because these are market prices for options. And I have a point that I want to reflect upon with you. These are market prices of options. Why would someone publish the market prices of options if they are given by a formula? The answer is that they are not. They're not given by the formula. What I told you about the Black-Scholes price of these options is interesting. It is not the price at which these options are traded. Okay, so I need to prevent that you suddenly think that I've been lying to you. I have not been lying to you. I've developed a mathematical theory, and I'm telling you that options have a price of their own. And frankly, today, no one uses the Black-Scholes theory to price options. Not like that, because the prices are published. You just look them up. Okay. So why am I telling you this? So at this point, there's many. Certainly, I have many things to say about how the real world works and why this theory was established. On the website, you have access to two very important documents. The one that is important right now is the Nobel Prize speech that Myron Scholes gave when he got the prize. He told us how the problem came to him. And I want to tell you what that was. When he was a professor at Stanford, a company, I think it was Wells Fargo Bank, went to him in the 70s, around 1970, went to him with a problem. The problem is the following. If I have an employee, say the CEO of a company, and I give him stock options, how much are those options worth? If a company is listed, Today, we know the price of those options because they're published. Back then, these options were not listed. In fact, options were the options exchange in Chicago had not even opened yet. Okay, so it was a valid question back then. Fast forward to today, one could say, well, the answer to that question is irrelevant because the options trade and you have the prices in front of you. So that would be true today. But imagine this. Imagine I give you options on a company that does not trade. Or options on a company whose options market is very illiquid and they don't have published prices. The thing is, the theory that was developed in the 70s still applies. And by the way, the reason these options started to be traded is because there was a way to price them. So the interest in pricing the options was there in the 70s. The solution came in 1973. That's when Scholes wrote his paper. Around the same time, the Chicago Options Exchange opened up, and then options could be traded because people had a reference price. You could trade them. And you can see when they were too cheap or too expensive, but still people traded them. No one will trade an option using the Black-Scholes as the price. Because if the seller doesn't want to sell at that price, what do? Take them to court because they don't want to offer you the Black-Scholes price? No. The Black-Scholes price is just the way to calculate the price, but it doesn't give anybody the obligation to trade at that price. So the market developed on its own. The Black-Scholes price was used as a benchmark at the beginning. That gave people an idea if they were overpaying, underpaying, and by how much. So, but once the market develops, the market is more powerful than any formula. And that's one thing that I need you to understand. It doesn't mean that formulas are useless. It means that formulas have a reason to exist, but it's perhaps not what many people think. Okay? That's the first observation that I want to make you. Of course, if you're dealing with a company without options or a company that does not even trade, for example, if you have your own startup and you give options to a friend, which is the original problem that Wells Fargo went to Myron Scholes with, then you don't have this table in front of you. Chicago Board of Options Exchange have not heard of your company, so you have to have another way of valuing them, and the Black-Scholes is a very good way to do that. Okay, but there's a very good additional reason why the Black-Scholes theory is still used despite the fact that you know the option prices, and that is the volatility. When you price the options, we need to have the stock volatility. Remember, the volatility and the interest rates are the two inputs that go into this. The interest rates are known. We know what they are. There's some speculation as to whether they will change or not. And the Black-Scholes theory for non-constant interest rates, it's different from what we saw here. That means that if people have different views as to what the rates will be, then they may disagree on the price. So that's one thing. But the biggest source of uncertainty when pricing options is the volatility of the stock. How do you calculate the volatility of the stock? You can argue that you have the stock price observations, so you can fit your Brownian motion to the stock price over the last, say, 5 years, and you get a certain volatility number, sigma, and that's the one that goes into the Black-Scholes equation. Once again, we're having a mathematical approach into the calculation of something, in this case the volatility. The market may not care. The market may think that the volatility ahead of us is much higher, therefore this option is undervalued. Which means that if you sell this option, maybe everybody will buy it from you. But no one will issue the option at such a cheap price if they think volatility is going up. That's where there is a market. Because the Black-Scholes equation, even if it was 100% accurate, even if it always works, even if you can have replicating portfolios without paying commissions, the uncertainty about the volatility is such that People disagree on the volatility, and that's why they trade options at a price which does not fit the Black-Scholes price at that volatility level. It will fit the Black-Scholes price at a different volatility level. And because of that, and this is, I hope, something you understand, because of that, people use the Black-Scholes equation to get the implied volatility for a stock, not for the price, because the price is already published. What is not published is the volatility. And this is great because the markets, what they are doing, they are giving you implicitly the value for the volatility of the stock. We call this implied volatility. So the minute you have options traded at a certain price, you have an implied volatility. Again, you think of the Black-Scholes theory equals a given price. So that is an equation with how many unknowns. You may think you know the volatility, but in practice, people don't think they know the volatility. They can calculate it from historical examples, historical time series. But if the market says something different, what people immediately think is that the volatility is not what history implies. It's not what statisticians will calculate. It's something different. And this is today the biggest use of the Black-Scholes theory. You use the Black-Scholes theory not to calculate the price, but to calculate the volatility. You may have heard of the VIX. The VIX is an index which is derived from the prices of certain index options. I'm just going to leave it like that, okay? This is a very good example of a situation where, morally speaking, not exactly speaking, but morally speaking, you use the Black-Scholes theory backwards. You go from price to volatility. And then that becomes a new security, which you can buy and sell in the market. What's the VIX there for? The VIX is there to measure the level of risk, fear, or stress in the market. Some of you are probably aware of this, and you know what I'm talking about. Some of you may not. So from now on, if you want to understand if there's fear in the market, what is Trump doing with the economy? Is this good for this? Is this good for that? Look at the VIX. The VIX is a very good level of the level of risk or fear or stress in the market. Far better than the price. The price you don't know. What you probably know stock prices today are at all-time highs. So is gold. Is that because people are very bullish, or is because they are concerned about something else? Sometimes we don't know. It could be that the US dollar is so cheap, or people think it's so useless, that the value of these commodities it just increases. So you need other ways to measure the market reaction to what's going on. And the VIX is considered to be a very good one for that reason. Okay. By the way, there's just in case, invested in the VIX as a way to hedge against fear is not a good idea. Okay, it's a good non-investable index. As an investable index, it's not so good, and that's something which, if you're interested, I can tell you. Maybe we'll talk about that when we talk about investments at the end of this course. Okay, but just want to give you as big a financial context as I can about the usefulness of the Black-Scholes theory. Okay. Generally, the VIX rises when stocks fall, and it declines when stocks rise. So, why? Because typically, when people are afraid, they sell stocks, and when people are bullish, they buy stocks. But that's not always the case. Sometimes it doesn't happen like that. All right. Along these calls and puts, there's other types of options. I have here Bermudan options, as an example to tell you. These are options which are neither, they are called Bermudan for humoristic reasons. It's almost a joke. Bermuda is considered to be between Europe and and America. And these options are somewhere in between. They can be exercised anytime prior to expiration, but only at selected times. So you have some freedom, but not a lot of freedom. That's why they're called Bermuda. Okay. You have Asian options. Asian options, they are called Asian for Asian reasons. Not a joke, by the way. What happened is that Asian markets still today are not very liquid. There is many stocks don't trade very frequently, and finding the price for certain stocks is you just have to wait months before a trade happens. Because of that, to issue a stock option on a value of a stock at a very precise point in time could be very dangerous. On the one hand, that stock price could be very stale. It could have been there for a long time. Even worse, that stock price could be manipulated. Imagine I sell you a stock option, or many stock options, millions of dollars of stock options with a, say, strike price of 100, and then 5 minutes before the market closes, what I do is I had some stocks that I bought before. I sell one stock. No one wants it. I sell it very cheap. I give it for free. Then that day, the price of the stock will be registered as near zero. So that will be a way for me that issued stock to you to pay you nothing. You understand what I'm saying? So stock price can be manipulated for stocks that hardly ever trade. So if that's the case, how do you defend yourself from that? How, imagine that I want to, I really, you really want protection and I'm happy to sell it to you, but you don't trust me. How would you trade that? So what you do is you make the payoff depend not on just one price, but on a collection of different prices. For example, I can have the option depend on the average of prices or the average of payoffs, or a strike with respect to an average a price over a week, for example. So if I want to manipulate the market to affect negatively your option price, then I'll have to manipulate the market a lot. So it'll be very costly. So this is a way for me to de-incentivize. And certainly I cannot, changing the stock price at one point in time is not gonna help. You see what I mean? This is typical for securities with very infrequent valuations, very low volumes, or even very high volatility, where things change so much that picking a price at a precise point in time is just risky. And that's where they call Asian, because in Asian, this is how you would do that. But for example, this is not only restricted to Asian securities. If I want to buy oil, if I want to buy, imagine I'm buying options on oil to Exxon for a very big amount. Exxon is a very big producer of oil. They have the ability to move the market on a given day. So if their options book with me is substantial enough, they may decide to just change the price of oil a little bit for 5 minutes. It'll have very little impact on their overall sales, but my option value will be zero. They can do that. So these are examples that I hope will bring you closer to the real world of option trading. And there you see that everything we've learned is really just a mathematical foundation on which everything else builds. But in many practical situations, the practical considerations will overrun any of the math we have done here. And this is part of the reason why I want to explain the math to you, but I want to tell you at the same time a very big disclaimer. Beware of all of these things, because in practice, you have to be very intelligent to trade these things. And what I'm telling you here is only part of the story. Now, alongside this, we also have some other types of derivatives, fixed income derivatives. Caps offer protection when interest rates rise over a certain ceiling. Floors, the opposite. If rates are very low, they'll still pay you something. So for example, if you have a pension and rates are very, very low, then you could end up earning very little from your pension. A floor guarantees some cash flow. A collar is a combination of a cap and a floor, basically guarantees that rates will always be within a certain band. Swaps, we see swaps in the future. Swaps, non-cross currency swaps, these are instruments that exist to give you protection against interest rates. So just like we have seen options as protection against option prices doing, sorry, against stock prices doing something, you have a whole universe of other options where they give you protection against interest rates, and these are fixed income derivatives. And frankly, this is almost a never-ending story. You could have you have lots and lots and lots of options which are there, and they're all one way or another treated the same way as what we have seen here. So now, from where we stand, from the hill we have climbed, you have an enormous landscape of options, futures, and other transactions whose prices will have to be developed. And when you do, well, you just get to work. Everything we have learned here will be useful, but you have to replicate that infinitely many times to deal with the infinitely many variations that exist of infinitely many financial products. And that's why I do my course in condensed form, because the applicability of what I'm talking about here is limited, but the concepts we have developed, they are good forever. Okay? You will have to redo this in many different contexts in the future. Okay. I think we're going to take another break, 10 minutes. When we come back, I'll tell you about some of the other applications of the Black-Scholes theory, which is going to get us closer and closer to the topic of risk management, which I will start 2 weeks from now. Okay? Let's take a 10-minute break, and when we come back, we talk about Greeks. Okay. I think we can continue. What I'm going to discuss now is another. This is a very important. This is a very important topic, which is related to the Black-Scholes theory, but it goes well beyond the Black-Scholes theory. It's a way to understand the markets, which in the Black-Scholes context, we are now very well equipped to understanding because they give us such a powerful analytical toolbox. But the concept goes beyond that, and even in areas where we don't have the analytical toolbox, we want to understand the following very important question. Imagine you have very simple situation. You have an option price, you have a certain price, but then I tell you, what were your assumptions? Well, I'm assuming that the volatility is equal to this. What if you're wrong? What if the volatility is something different? Oh, well, then the value is something different. Okay. Your assumption is the stock price is what it is now. Sure. What if the stock price was something different? Then you can say, well, how can it be something different? It is what it is. So yes, I know, but what if tomorrow it's drastically different? Something happens. What would the price be? Oh, well, let me look. Maybe it goes up, maybe it goes down by this much. This is very important when we do risk management because sometimes we're making assumptions and we value the portfolio under certain assumptions and we want to know what if our assumptions are wrong? What if market conditions suddenly change? Or even the expression that we have for the price is very complicated. We know what the price is, but conceptually, it's perhaps hard for us to understand how things will change between today and tomorrow. Yeah. In math, when we want to understand how things change relative to parameters, which may be unknown or uncertain, we use a derivative approach. A derivative is precisely that, is the tangent to the line. So if things move like that, I expect things to move proportional to that. And that is what the derivative is. So a Greek is a amplified concept of derivative of prices, portfolio valuations, as a function of parameters that may be uncertain or unknown. The most important one is the delta. The delta of an option or the delta of a portfolio is the derivative of the price with respect to the underlying price. As I said earlier, if the stock now is something, the option price is something, but if it was something else, then what would that be? This is important, for example, because between today and tomorrow, the impact of time on the option price is very small. It's known is very small. On a call option, for example, it's very small. If you're far from maturity, it's very small. If you're close to maturity, it's very big. But if you're far from maturity, it's very small. But the impact of the stock price could be large. And that proportionality, that change of the option price with respect to the option is something which is very important to take into account because this is going to be your major source of risk, the change of the underlying stock between today and tomorrow. Of course, if you're hedging, that this doesn't matter to you. But oftentimes these options are issued and you don't hedge constantly, because once you move into the real world, every time you buy and sell, you lose something. It's called slippage. No one works for free. We are making that assumption today, but in the market, sometimes you don't want to be constantly buying and selling as the stock goes up and down. You're gonna go bankrupt just on transaction fees. So to have some idea about the price of the option when the stock changes is very important. If it changes very little, that's good. Then you're probably not going to take action, which will cost you money. But if it changes a lot, you better do it. So that's one of the options of the applications of the delta. The other one is the gamma. Gamma is the second derivative. As you see in finance, there is a nomenclature of its own to determine all of these quantities. So the gamma is the second derivative. Now the second derivative is, I'm going to explain all of this in detail to you in the half an hour we have left. Okay, but I want to give you some at least intuitive understanding of that. The delta is so important that the change of delta matters, and that's what the gamma is. And I'll give you some examples in which the gamma can be dramatic. Some of you may be familiar with a term that has been, I think, introduced for the first time during GameStop, the gamma squeeze. Have you heard of that? Anybody has heard of the gamma squeeze? Well, it's related to this. So I'll tell you a little bit about that in a few minutes. Vega is another important, it's not a Greek, by the way. Vega is not a Greek letter. All the others are, but not Vega. That's the derivative with respect to volatility. We saw that earlier, and it's coming up today with a very precise name. Vega is the difference in the option price if the volatility is something different. Given that the volatility is not observed, this is a very important object. It tells me the underpricing or overpricing if the volatility assumptions are wrong. Very important. Rho is another Greek letter, and that corresponds to the change of the option price as a function of the interest rates. If interest rates go up or down, how would my option price change? The theta is the change of option price with respect to time. As time goes, the theta will measure the change in the option with respect to time. When I'm far from maturity, this number is very small, but when I'm close to maturity, it could be high. Okay, so this is a formalism which, in the context of the Black-Scholes theory, is very nice because all of these things can be calculated. The solution being a differential equation of a different type. You can solve them. Okay, but they're used also in contexts where the Black-Scholes theory does not exist, and perhaps they cannot be calculated, perhaps they can be estimated. It gives us a very good 5-dimensional view of the valuation process, taking into account the variables that matter the most. So I have here a graphic of how these Greeks can be visualized. And this is a very important factor for people who manage portfolios, even people that trade options. When you drive your car, you know that if you go faster, then you arrive sooner to your destination. It also increases the probability you get a fine if you go over the speed limit. These are things that we know. Intuitively, we know how our actions would affect the outcome of what we're aiming for. When we have options, we need to have that control mechanism too. We need to understand, if I wait, how will that option value affect me, or if something happens in the market. This gives us that. So let me look into this with some detail. In detail, this is what the delta is. It reflects changes in prices. And again, this is not only for options, this is for portfolios. We will see this when we look at investments, for example. This will show up there. Okay, so it is a derivative of the value of my portfolio with respect to the risk factors. So even if I have more than one factor, I mean, we saw earlier in my first definition the value of the underlying as the risk factor, but I could have a whole vector of risk factors, in which case the partial derivative becomes a gradient, okay? And the delta is usually a gradient. I usually have more than one risk factor, and it's the value of my option or my portfolio with respect to all of the risk factors taken into account at the same time, okay? I have here an example. This is how a delta, according to the Black-Scholes model, looks when we have an option portfolio. So let's look at that. This is very interesting. This is the portfolio at maturity. That's time zero, you see? This is wrong. This is zero. This is backwards, okay? This is backwards. Okay, I just realized that. So look at the value of my option, and this is the value of the underlying. Look here. I hope you can read the three-dimensional graph. This is my option price at expiration, where this is my strike price. You see, what you see there is exactly the derivative of my option payoff. My option payoff is that. The derivative of that is exactly that, 0 and 1. It's exactly what we see there. That's at maturity. At maturity, the time to maturity is 0. As you walk away from maturity, look how smooth the curve is. So it still likes to look like what it will be at maturity, but it becomes more mellow. It has the biggest delta right there when you're at the money. Typically, at the money options have the highest delta value. That has the highest delta value. Okay, so you can see that here the portfolio does not change very much, and here it does change very much. So that's the 3D. Of course, in the Black-Scholes theory, I can calculate this. For portfolios without a Black-Scholes theory or equivalent, it's crazy to have or to claim that we can have such a detailed graph. This graph is done by a computer because I have a semi-explicit pricing function. Okay? So that's how the delta of the option looks like. Okay, let me go to the gamma. The gamma is the second derivative. In the case of real option, because real portfolios, I have not only one risk factor, I can have many risk factors, and then in which case it becomes a matrix. So typically the gamma is a matrix. But I'm going to show you what this is in the context of a single risk factor, which is one of the most beautiful option equations, excuse me, that exists. Look, can you explain that? Here, the time to maturity is also wrong. Okay, it's the other way around. Can you explain that? What is that? This is a call option. A call option, the payoff is like that. So its derivative is, I'll do the derivative in a different color now. I want all three in the same graph. Its derivative is like that. And its second derivative is what? Is 0, infinity, 0. You see that? That's what this derivative and second derivative would be for the payoff of the option. Well, that's exactly what we have there. That's infinity. So this is interesting because, of course, this is, and then, of course, it becomes smooth and, and all of that. It's interesting because gamma gets to be very high when you're very close to expiration and very close to being at the money. In fact, it becomes infinity. And for that reason, when you have options, which are at the money and you're close to expiration, they could generate a very large amount of trading volume. So if you're familiar with the term gamma squeeze, this is what happens when you have an option that has very big volumes generated by a lot of option writing on those options because you're close to maturity and you're close to strike. Look at the gamma volume is here is zero. There's nothing there. It's only here. It's only here. Okay. Now, for example, when a few years ago and in January, we're in February now, but in January, but more or less around the same time is when the GameStop event happened. And I was asked, coincidentally, by the students back then what a gamma squeeze was. But that was a week before I was doing this, so I couldn't fully explain. But now today I can tell you, in case you were part of that, this is what a gamma squeeze is. But note that this happens only under very, very precise circumstances. If the options that are written are not on the money, there's no such thing as a gamma squeeze. There's no gamma activity. If you're far from the expiration date or far from the strike price, there is no gamma activity, gamma-driven activity. Okay? And this graph is very clear. This is why I would like you to remember this graph. It's very meaningful. Very meaningful. Okay. So this is what happened in the year 2021. And again, it was exactly a week before this one. It was at the end of January. So as you know, GameStop was heavily shorted, exceeding 100% of the available shares. And Malvin Capital was the hedge fund, one of the hedge funds that was involved in that. There was a good rationale for being short a GameStop, but a group of people decided that they didn't like that rationale. In fact, they didn't like that a hedge fund was going short against the place where they do all their game shopping. So they somehow, Wall Street Bets discussed GME as a potential short squeeze candidate. It was not, but it became one just because there was a social movement that developed around that. So they aggressively bought cheap out of the option call options. They were very cheap and they're very out of the... When you take an option which is very out of the money, they're very cheap because no one thinks that prices will go there. But once they do, then what happens? Once they do, then the market makers who sell options had to hedge by buying those shares. And as you approach maturity and you approach the strike price, then you have to buy many, many more. And if they're heavily shorted and you have to buy a lot of shares, they create a market squeeze, a short squeeze situation, which we'll describe in detail in a few weeks. Okay, not now. And this created, well, presumably, this created a very large trading volume for GameStop shares around the time when these options presumably expired. Now, I don't have that information. I don't know if this is all true. This is what was mentioned in the forums. I don't have a way to check. It agrees somehow with the concept of a gamma squeeze, but you need to have very precise conflagration of many events. The strike price has to be the same, exactly the same, very similar to the ones at which these out-of-the-money options were issued. I doubt that was the case. Could be, maybe for some of them. You have to be very close to maturity, which means that the options should have been issued exactly on that Monday, which I don't know if that was the case, or Tuesday or Wednesday, something like that. I don't know if that's the case. It's consistent. It could be, but I don't have enough information to tell you that it was actually true. A lot of this was chatter on social media. But if that is true, it is true that short sellers were forced to buy back shares. And this is what's called a short squeeze. Because they have to buy shares at very high prices, and they could be very hard to find. And then they will pay enormous amount of money for that. So this is when markets get inflated because of the short-term need of the short sellers of those stocks. And that created a feedback loop. So this creates a feedback loop. We will see situations where I have enough data so I can tell you that this actually happened. In the case of GameStop, I suspect it happened because of what was mentioned, but I couldn't find independent verification of that. Okay, but what it is true is that GameStop price jumped from $20 in early January of 2021 to an intraday high of $483 on January 28, 2021. So as you can see, just a week before I typically teach this class. So that was anyway, I now get to tell you after the fact what happened there. Okay, this is not the only one. Tesla also has been, and other companies, and Volkswagen is the one that we will discuss in great detail when we talk about investments, because Volkswagen will be important for us for other reasons. Okay, all right. So, all right. So this is I explained here. If you hedge an option and you need to, when you hedge an option, if you go back to the Black-Scholes theory that we developed today, you would remember. You may remember, go back and check, that the number of units I need to have is exactly the delta. Okay? Remember the replicating portfolio? The number of stocks I was supposed to buy was the partial derivative of the option price with respect to the underlying. That's exactly the delta. So the delta represents the size of your stock portfolio if you're hedging the option. So what is the trading volume? The trading volume is the change of stocks. If I have to buy a lot of stocks, and the number of stocks I have is the delta, then that's the derivative of the delta. So the trading volume is given by gamma. Okay? This is the trading volume implied by the rehedging of the option according to the Black-Scholes price. You see, this you can only see in the Black-Scholes concept. Sorry, in the Black-Scholes context. In other portfolios, who knows what they will be. But in the Black-Scholes theory, we know that the hedging portfolio holds delta units of the stock. So the trading volume is gamma. How many stocks you have to buy and sell? That's the derivative of delta with respect to the underlying. That's gamma, right? That's why if gamma is large, then the trading volume will increase. And this is what is known, that large gamma creates large transactions. If a stock is heavily shorted, then these large transactions will create a short squeeze. Another word for a gamma squeeze. Okay? All right. So and again, this is an explanation once again of the graph that we saw earlier. The option payoff is that, so the derivative is that, and the gamma close to expiration would look like this. And because the trading volume is gamma, then this creates an increase in the trading volume. Okay, so these are the other ones. I already explained them. I don't have any new information to give you. I think I'm just going to just check if I have something. No, I have some nice pictures. This is how the Vega looks for a call option in the Black-Scholes model. We can see here some features, which is as we're close to, again, all of these are wrong. I don't know why that happened. But as I'm close to maturity, then the volatility impact is negative. So it's negligible. We don't care. But as we get away from maturity is when the volatility really affects the price in a very big way. Options are insurance contracts on the price of the stock. So the further you are, the higher the volatility it is, the bigger premium you'll have to pay for the protection that the options give you. So this chart is intuitive. You just need to think of the option as an insurance product. Okay? So have that. This is a mistake. This is theta. So theta measures the sensitivity of the value of the portfolio with respect to time. So we already discussed that, nothing new there. And rho measures the sensitivity of the portfolio with respect to interest rates. We went through that, nothing new there. Okay, I will end today with an example of how one can use this way of thinking, not to predict the demise of Silicon Valley Bank, but we're getting very close to starting the risk management part of this course. So I want to tell you how this thing that we discussed here is related. Oops, sorry. I want to talk about how this thing we did here can be used to understand things that happened in the in reality. So I'm going to show you how this could be applied to the case of the Silicon Valley Bank bankruptcy. I assumed you know what I'm talking about, Silicon Valley Bank. Okay. There you go. So what I have here is a schematic of what these derivatives are. So this is the delta. Oops. This is the delta. It's the linear approximation. And that's the gamma. I'm not interested in the gamma for the Silicon Valley Bank. I'm only interested in the delta. And I'm going to do a very simple heuristic calculation so you can see the situation. So these were the situation of Silicon Valley Bank. It had deposits from venture capital groups, and all of the deposits were invested in what's considered to be the safest investment possible, treasury bonds. The duration was about 10 years of those treasury bills, long term. But interest rates went from 0 to 5% in a very short period of time. So if interest rates go from 0 to, oh, by the way, what's the duration? The duration is the delta with respect to interest rates, okay? You may be thinking, oh, that was raw. Well, for options, it's called raw, but when my portfolio bonds, for example, the risk factor is interest rates, that's the delta. But fine, you can call it raw also, okay? Usually, if delta refers to the risk factor, the risk factor of bonds, then the delta will be with respect to interest rates, but you can say it's raw, no problem, okay? Either will work. But it's 10 years, that duration. So if interest rates jump 5%, by Taylor's theorem, I would expect to lose 50% of the value of my portfolio, right? Maybe you should take into account the gamma because that's a very big change, and the delta only measures small changes. It's a linear transformation, or a linear approximation, right? The gamma is a bit more exact, it's quadratic, but just the delta will imply a 50% loss on your portfolio. Now, banks are typically leveraged. So if and the Silicon Valley Bank was not very leveraged. Banks can be leveraged 40 times. They were only levered 10 times. But if you lever 10 times, the 50% will turn into 500%. So from here you can see, this is heuristic. This is not a formal derivation, but from here you can see how Silicon Valley Bank was killed by the gamma of the portfolio. This killed it. It's not very big, right? Compared to what happened in history. We'll talk about this in 2 weeks. So this actually killed two banks, Silicon Valley Bank and Credit Suisse. Here, and again, I'll go through this in 2 weeks. Here, there were 6 bank failures. Per year. Imagine that. This is what gave rise to the derivatives market, actually. That was before derivatives. This tremendous financial situation gave rise to the derivatives market. So, but we'll deal with that in 2 weeks. So we seem to be going back in time. It's just that I have to tell you the history of risk management. I'll do that in 2 weeks. Okay. You know what? I think I'm done. I will leave it here. Next week, I will be telling you some formal derivations of formal treatment of Brownian motion. We will be discovering some of the properties, characteristics of that, and I will explain to you Monte Carlo methods. So a bit of probability next year. We're going to need it for risk management, but also for your own sake, because Monte Carlo is something which is of independent interest.